Hello, everyone. Now, let me give you a brief overview of our work. Graphics Capsule, learning hierarchical 3D face representations from 2D images. Humans are easy to construct the hierarchy of objects by only observing them. Our work aims to investigate the similar perception mechanism of neural networks in this paper. We propose the IGCNet to learn the hierarchical 3D face representations from large-scale unlabeled in the wild images. Whose primitive is the graphics capsule that contains the 3D representations with explicit meanings by combining depth and albedo information as cues. IGCNet successfully decomposes the objects into a set of part-level graphics capsules and constructs the hierarchy of objects by assembling the part-level capsules into object-level capsules. IGCNet reveals how the neural networks oriented at visual perception understand faces as a hierarchy of 3D models. Besides, the part-level graphics descriptions can be used for unsupervised face segmentation and interpretable face analysis. Now we will give more detailed illustrations about our work. First, the motivation. It is commonly recognized that a path toward autonomous machine intelligence is to enable machines to have human-like perception and learning abilities. After observing a large scale of unlabeled images, previous methods successfully decompose the digits or faces into a set of parts. However, this strategy performs well when the objects are intrinsically 2D, like handwritten digits and frontal faces, but has difficulty in interpreting 3D objects in the real world, especially when we want a view-independent representation. As for how to represent the perceived objects in computer vision, one of the most popular theories is the Marsh theory. He believed that the purpose of the vision is to build the descriptions of shapes and positions of things from the images and construct hierarchical 3D representations of objects for recognition. In this paper, we try to materialize Marsh's theory on human faces. Thus, we propose an inverse graphics capsule network IGCNet, whose primitive is a new type of capsule, graphics capsule, that is defined by computer graphics to learn the hierarchical 3D representations from large-scale unlabeled images, as shown in the figure. The hierarchy of the objects is described with the part capsules and the object capsules, where each capsule contains a set of interpretable parameters with explicit physical meanings, including depth, albedo, and pose, when an IGCNet is well trained. The learned graphics capsules naturally build hierarchical 3D representations. The details of the training will be introduced next. During training, the input image is first encoded to a global shape and albedo embeddings, FS, which are sent to the GDM to get the spatially decoupled part-level graphics capsules. Then, these capsules are decoded by a shared capsule decoder to get explicit 3D descriptions of parts, depth, albedo, and 3D pose. Afterward, the parts are assembled by their depth to generate the object capsules as the object-centered representations. Finally, the 3D objects embedded in the object capsules are illuminated, posed, and rendered to fit the input image, following the analysis by synthesis manner. To decompose the global embedding of the image into a set of semantic consistent part-level descriptions, we propose the graphics decomposition module taking shape decomposition as an example. GDM maintains M-shape basis WM as the implicit part templates. Given the global embeddings, GDM performs cross-attention between the global embedding and the basis to get M-disentangled D-dimensional embeddings. After that, we perform an MWay1 hot attention vector is generated for each of the D dimensions to further reduce the entanglement and generate independent part-level embeddings. The same pipeline is applied to the albedo embeddings, where the only difference is that the attention is copied from the shape embeddings. which ensures that the shape and the albedo information are decomposed synchronously. Here are the loss functions to train IGCNet, which include several constraints for reconstruction, semantic consistency, sparsity, and background separation. Next, we will briefly introduce the experiments. The graphics capsules learned by IGCNet provide a face hierarchy with explicit graphics descriptions. Here is the discovered face hierarchy. By incorporating shape and albedo information as cues, the face images are naturally decomposed into 6 semantic consistent parts: background, eyes, mouth, forehead, nose, and cheek. Based on the aforementioned 3D face hierarchy, we apply IGCNet to validate the advantages of such hierarchical 3D descriptions and uncover the face recognition mechanism of neural networks. To evaluate the view independence of 2D and 3D representations, we compare our method with the 2D autoencoder with the architecture and the training strategy same as ours. It can be seen from the figure that 3D presentation achieves better accuracy in this cross-view recognition task. Besides, we further analyze the representation consistency across views by computing the similarity matrix of representations under different views. It can be seen that our method shows better consistency, especially when matching images across large views. Furthermore, we designed an experiment to explore which part-level graphics capsule is crucial for face recognition and which component shape or albedo of the capsule is more important. After assigning the part-level shape embeddings and albedo embeddings with trainable non-negative scalars as attention weights, we send them to a linear classifier for recognition. The results show that the albedo is more crucial than the shape when recognizing faces. The albedo of the eyes is the most important component and the shape of the nose is more important than the shape of other parts. To execute the quantitative and qualitative evaluation, we compare IGCNet with other unsupervised segmentation methods. The quantitative and qualitative comparisons validate that our method outperforms other methods with better semantic consistency. That's all for the report. Thanks for listening. If you have any questions, please contact the following email.